This video is on Euler's formula, which leads us when we substitute in a particular value for the variable to Euler's identity, which is one of the most elegant identities in all of mathematics. It's named after Leonhard Euler, Swiss mathematician who contributed enormously to mathematics. And it states the following: e to the I theta equals cos theta plus I sine theta. And Euler's identity comes when we substitute 0 for theta into this equation, giving us e to the I pi equals minus 1, which can be restated as e to the I pi plus 1 equals 0. One of the reasons this is so elegant is that it combines all of the most fundamental values in mathematics: 1, 0, e, pi, and I, the root of minus 1. Before we get into this formula, a little bit about Leonhard Euler, the man who was responsible for it. Euler was born in Basel, Switzerland on the 15th of April 1707 and died on the 18th of September 1783. Throughout his lifespan, he was extremely prolific, producing hundreds of first-class publications and earning the respect of his contemporaries, being regarded as one of the greatest mathematicians of the 18th century. One of his nicknames or titles was Analysis Incarnate, and within mathematics he worked across multiple fields: geometry, mechanics, graph theory, topology, analysis, number theory, complex analysis, and calculus, and not just within mathematics but beyond the bounds of maths. He was a physicist, an astronomer, a geographer, a logician, and an engineer. So he truly was what we would talk of today as being a polymath. One other caveat before I get into this is that this video is by no means any kind of comprehensive or exhaustive inquiry into this formula. If you want to do that, you can by all means do that and search for that type of thing. And I would recommend highly one channel on YouTube for that. That would be 3 Blue, 1 Brown, which was created by Grant Sanderson. And he has done at least 2 videos on Euler and this formula, which I have linked to right here, if you want to have a look at, to his channel and to the particular video. This would give a far more comprehensive analysis of what this formula actually means. The purpose of my video is merely to just show the link between the exponential and the trigonometric in 2 ways. But once you've seen this and you want to learn more or consider more deeply, please have a look at this channel by Grant Sanderson, as it will give you plenty of food for thought. Let's start by having a look at the exponential growth curve y is equal to e to the x. If you're familiar with this curve, you'll know that it's almost, as it moves along, almost horizontal as we move in the direction of the positive x-axis until it reaches a point where it noticeably begins to curve upward, and then it shoots off almost asymptotically. That point of change is often a point of interest in analysis of this type of growth. But just for the sake of consideration, let's have a look at a little table here I've made with the positive values of x. We can see from x is equal to 0, what we get is y is equal to e to the 0, which is 1. And that's reflected graphically in the curve crossing the vertical axis, the y-axis. It crosses at 1, so the coordinates of that crossing are 0, 1. If we look at x is equal to 1, the y value is approximately 2.7. We can see that with the first dotted vertical line, 1 unit across from the y-axis. If we look at x is equal to 2, we get an approximate value, which is now off the graph here, of 7.4. For x equals 3, we get a value of approximately 20. For x equals 10, we get a value of approximately 2,200. And when x equals 100, we get a value of 2.7 times 10 to the 43, which is a 1 with 43 zeros after it. So the growth of this curve is phenomenal once we begin to get into larger values of x. And correspondingly, if we now look at the second table for negative values of x, we can see if we take negative 1, y is equal to 0.37. And if we take negative 2, y is equal to 0.14. And for negative 10, we get 4.5 times 10 to the minus 5. And as we move outwards to the left, negative 100, we get 3.7 times 10 to the minus 44. So almost negligible to have any to register on a scientific calculator. And as for minus 1000, we simply get an error because it's indistinguishable from 0. But it will always be, however insignificant, however infinitesimally small, it will be greater than 0 across the entire set of real numbers. So that leads us to say y is equal to e to the x is greater than 0 for all x on R. And so that's one element that makes this equation interesting, because when we have e to the I theta and we substitute pi into that, we get e to the I pi equals minus 1. So suddenly we have, for some function which is always greater than 0 across the entire spectrum of reals, we suddenly get a negative value. That isn't exactly what we're investigating here today, but it's just something of interest to consider. Coming up to Euler's equation, we now have e to the I theta equals cos theta plus I sine theta. Substituting for theta with pi, we get our second line, e to the I pi equals cos pi plus I sine pi, which we know cos pi is minus 1 and sine of pi is 0. So that gives us e to the I pi equals minus 1 plus I times 0, which allows us to arrive at Euler's identity. E to the I pi equals minus 1, which is equivalent to e to the I pi plus 1 equals 0. Again, as said before, one of the most elegant equations in all of mathematics. It combines the most fundamental values in maths, 0, 1, pi, e, and I, the root of minus 1, in the most simplistic and elegant way. Now that we've gone through the setup, here's our first proof that relates the exponential on the left to the trigonometric on the right. Okay, let z equal cos theta plus I sine theta. Now, first step is to take the derivative of z with respect to theta, since z is a function of theta. dz on d theta is equal to minus sine theta plus I cos theta, because we know that derivative of cos is minus sine and derivative of sine is cos. So, next step is to factor out the I. But first, before we do that, notice that minus sine theta is the same as I squared theta. So we have effectively I squared sine theta plus I cos theta. When we remove the I, we get I into I sine theta plus cos theta, which is the I into cos theta plus I sine theta, which equals IZ. So dz on d theta is IZ. Notice that when we take the derivative, we simply have the original function multiplied by the coefficient. Continuing on with the last point from the previous slide, we notice that if we have the derivative of a function being equal to some multiple of that function, then we can write the original function as an exponential. So, for example, if we have function theta equals e to the a theta, when we take the derivative, f dash theta, we get the coefficient of theta multiplied by the function, a e to the a theta, which is equal to a times f of theta. So that applies here to the left. So on the left we have dz on d theta is equal to iz. Now we're going to treat this like it's a separable differential equation. So we're going to move d theta to the right, and we're going to bring z over to the left. So we end up with dz on z is equal to I d theta. Now the next step is to take the integral of both sides. Moving on to the next step, taking the integral of both sides, on the left-hand side we get the natural log of z is equal to, on the right-hand side, I theta. Then, from that, onto the next step, we recognize that if we take the exponential of both sides, that gets rid of the natural log on the left, so we have z is equal to e to the I theta. And recall that we started out with z is equal to cos theta plus I sine theta. So here we've shown the relationship between the exponential function and the trigonometric functions. E to the I theta is equal to cos theta plus I sine theta. Here's the second proof of e to the I theta equals cos theta plus I sine theta, this time using differentiation. So if we set f of theta equal to e to the minus I theta into cos of theta plus I sine theta, we'll now begin with the first step, which is differentiating this. Recall that this is a product, so the product rule applies as we see down below. If f of x is equal to g of x times h of x, then f dash of x is equal to derivative of the first times the second plus first times derivative of the second, which is g dash x hx plus g of x h dash x. And another way of writing that is d on dx g of x times h of x plus g of x times d on dx h of x. And in the case of this function, that is f dash theta is equal to d on dx e to the minus I theta times cos theta plus I sine theta plus e to the minus I theta times d on dx of cos theta plus I sine theta. So continuing, we've just finished that second line. Moving on to the third line, we have d on dx of e to the minus I theta is minus I e to the minus I theta times cos theta plus I sine theta plus e to the minus I theta. Now, take the derivative of what's inside the brackets with respect to theta. Cos theta becomes minus sine theta. I sine theta becomes I cos theta. Now, recognize the coefficient of sine theta. It's negative, or minus 1. That is interesting because we can replace that with I squared. Let's have a look at the next line, and I'll show you where that comes from, where that appears. Next line, minus I e to the minus I theta times cos theta plus I sine theta plus e to the minus I theta. Now in brackets, instead of minus in front of that sine theta, we have I squared sine theta plus I cos theta, because minus 1 is equal to I squared. Now, as we go on to the next line, we will clean up what's in the brackets there with that trigonometric expression so that it's the same in both sets of brackets. So we have minus I e to the minus I theta into cos theta plus I sine theta plus I e to the minus I theta. So we've drawn a factor of I outside of those brackets, leaving I sine theta plus cos theta. Now we move to the final line. Minus I e to the minus I theta into cos theta plus I sine theta plus I e to the minus I theta. Swapping those two terms round, cos theta plus I sine theta. So this leads to the next slide. So we've almost finished. If you look at this now, you'll recognize we have a common factor in this expression, which is cos theta plus I sine theta. And on the left-hand side, the coefficient is minus I e to the minus I theta. On the right-hand side, the coefficient is I e to the minus I theta. Those two cancel each other out. So what we in effect have in the second line there is negative some quantity plus positive some quantity, thereby in the third line giving, if we factor minus I e to the minus I theta out of it, 1 minus 1. So we have 0 times cos theta plus I sine theta equals 0. So that shows us that f dash of theta is equal to 0. So if the derivative is equal to 0, that means the original function must be a constant. So that now leads us to assume that we can substitute a value for theta into this to work out what that constant value is, or what that constant function is. So suppose we take theta equals 0, what do we get? Well, the original function, we know what it was, I'm not going to repeat it. We get e to the minus I times 0 into cos 0 plus I sine 0. So what do we get? Function of 0, f of 0, is equal to e to the 0 times, in brackets, cos of 0 is 1, and sine of 0 is 0. So we get 1 times, brackets, 1 plus 0, which shows that f of 0 is equal to 1, so f of theta is identically equal to 1. Having our function identically equal to 1 gives us the first line. The next step here, and the final step indeed, is to multiply through on both sides by e to the I theta. So now we have e to the minus I theta, cos theta plus I sine theta, times e to the I theta. The two exponents cancel out, so we're left with cos theta plus I sine theta on the left-hand side is equal to, multiplying on the right-hand side, e to the I theta, which gives us the formula that we were looking for. Again, don't forget to check out Grant Sanderson's channel, because it gives a fantastic investigation into what this really means in far more depth than I've been able to do. As always, thank you for watching. I hope this has been useful. The whole purpose is to help people and to make things clearly understandable. So if you enjoyed this, give it a like, and please feel free to subscribe, as I'll be producing more videos regularly. Thank you very much.